we're going to spend some time learning how to count. Well, now, I mean, I know we already know how to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but sometimes we get really big numbers, and it's hard to count just by counting like that. So we're going to use in combinations of numbers. So we're going to use these things called factorials, and when we're dealing with probabilities, we're going to use permutations and combinations. So I'm going to remind you of a couple things that we learned before. One is that if you see the word or in a probability, it generally means that you're going to add probabilities together. If you see the word and in a probability, that generally means you're going to multiply, M-U-L-T-I-P-L-Y. So we're going to spend most of this discussion here talking about and. So we're going to go to the fundamental counting principle. This is part 2 of the fundamental counting principle, which deals with the word and. And it says, if I have event A and it has m number of outcomes, and I have independent, important word, event B, and that has n outcomes, then the total number of outcomes in event A and B is m times n. I did kind of a simple example of this for you earlier in a slightly earlier lesson, where I was talking about, the magic bowl, and I have all the different sticks with people's names on it, and let's say that there's 20 students. So the chance of you being called event A is 1 out of 20. And then I put your name back in, and you get another stick. You say now the bowl has 20 sticks. And I want to know, what are the chances I'm going to pull your name a second time right in a row? And the chances, the probability for that independent event N is 1 out of 20 in an independent event B. And so the chances of you getting called twice in a row is M, 1 out of 20, times N, 1 out of 20, is 1 out of 400. That's an example of the fundamental counting principle, part 2. Let's just take a very slightly more complex problem. And you're going to choose an outfit to wear. And first you're going to select your pants, and you have a choice between blue jeans or black pants. So your bottoms, there's 2 possible outcomes. And then you're going to choose a top, and it's either going to be red, green, or blue. So your top, there's 3 choices for that. How many ways can you put these together? Well, this is our M, this is our N. I have 2 times 3. There are 6 different outfit combinations that you could have here. And here's how it looks if you make a little tree diagram, which is a very helpful tool. If I pick blue jeans, then I still have a choice of red, green, or blue shirt. So that would make 3 different combinations of outfits. Jeans with a red shirt, jeans with a green shirt, jeans with a blue shirt. Or I could pick black pants. I still have the same 3 choices of shirt, so that I could have pants and red shirt, pants and green shirt, pants and blue shirt. Total of 6 outcomes. Now that one was pretty easy to draw, but we don't even have to get barely a little bit more complex, just a tiny bit more, and drawing a picture really becomes impossible. And that's where we want to rely on this fundamental counting principle. So here's an example where I want to go and get something to eat for lunch, and I have a choice of sandwiches, and it looks like there's 6 different choices of sandwiches, and I want to get a side item, chips, potato salad, fruit salad, a garden salad, 4 of those, and I have a choice of 5 different drinks. Well, that seems like a lot of combinations, and in fact it is. It's 6 times 4 times 5, our fundamental counting principle, M times N times what we'll call this P. and that equals 120. 120 different menu possibilities I can get from just these few selections here. So you can see how the fundamental counting principle is going to become very helpful when we're dealing with lots of choices. Now, sometimes I have counting situations and where it's really important that the order of the different items that I'm counting, that's really important. So, for example, let's say there was a student election. And there's going to be a president, a vice president, and a treasurer. Well, the order, I mean, just thinking that this is like the number 1 person, the number 2 person, and the number 3 person, the order matters here. And that is going to, if the order matters, I'm going to be dealing with these things called permutations. Don't worry, more examples coming along soon. Sometimes the order doesn't matter. So I have a bunch of books, and I want to know, well, how many ways can I arrange them on my shelf? But I don't really care about the order, so that's going to use a combination. Let's just take another quick example of the difference between permutations and combinations. We'll get into it a little bit more deeply. But I want to do a permutation of the 3 letters A, B, C. Well, permutation order matters. So I could have ACB, BAC, BCA, CAB, CBA. I have 6 different possibilities. My original 1, 2, 3, 4, 5, 6. 6 possible ways, 6 possible permutations. But if I don't care about the order, well, then I really just have ABC. Doesn't matter what order it's in. I only have 1 combination. And you'll notice that the number of combinations is always less than the number of permutations. Permutations always greater than combinations. Let's examine another thing about permutations. So let's say I have 4 friends, and I want to put them in a line. I want to put them in order, right? And I want to find out how many different ways can I put them in a line. So order is mattering in this particular case. You know, I want to see how many different ways I can line them up, all 4 of them. So I'm going to use a permutation. So the first person I pick, there's 4 different people I can pick to put the first way. And then after I pick that person, then I have 3 people left to choose from. And then I only have 2 people left to choose from. And then I only have 1 person left to choose from. So I'm going back to the fundamental principle of counting. I'm going to go to the fundamental counting principle. I had 4 choices times the next was 3 choices, times the next was 2 choices, times the next was 1 choice. So I have 4 times 3 times 2 times 1, and that tells me there are 24 different ways I can line them up. There are 24 permutations to line up my friends. This type of multiplication, where I start with a particular integer, and then each integer after that is decreased by 1, is called a factorial. And in this case, I have 4 factorial. I'm starting with 4, and I want to multiply it by every number all the way down to 1. And the notation is 4 with an exclamation point. The exclamation point is letting me know that I want 4 factorial. Let's try one more example. I have 8 runners that are running in a race. And I'd like to know, well, how many different ways might they be able to finish this race? I mean, there's 8 people. There's a lot of different ways that they might end up finishing 1 through 8. So that's a factorial. That would be 8 factorial, which is equal to 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And you can put that into your calculator if you want all those multiplication things. And you would find out there are 40,320 different ways that they can finish this race. All of them, each of them are different because order matters in this particular case. Now, you can see the larger, and that's only 8 factorial. I can have to punch a lot of numbers into my calculator to do that, but there's a way to do it in your calculator that makes it simpler. I start with 8, and then I press the math button, and up at the top I have these different options right here. Math, numbers, CPX, PRB. I want PRB, that stands for probability. And I can either go over 3, or if I was back over at math, I could go to the left 1, and it kind of cycles around. And you'll notice that number 4 right here is an exclamation point. So I would go 4. What happened to my calculator? There we go, I got it back. 8 factorial, press enter, 40,320. So now we know what factorials are, and we know an easy. So there are 40,320 permutations of my 8 runners. Well, though, if you think about a track meet or any kind of a race, usually you're not that concerned with the order of all the runners. Usually you're only concerned with maybe like the top 3. The top 3 are running in the league championship, and the top 3, they're going to go to the state championship. And I would like to know, well, how many different permutations are there only of the top 3? Well, that's going to be 8 times 7 times 6. That's going to be my first 3 finishers. And that's going to equal 336. So it's just like I had started with all 8. But I said, well, really, I'm only interested in the top 3. I'm going to get rid of 5, 4, 3, 2, and 1. So really, I want you to think about this mathematically. It's really the same thing as if I took 8 factorial, which is equal to 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and I divided it by 5 factorial, which is 5 times 4 times 3 times 2 times 1. Because then the 5s, 4s, 3s, 2s, and 1s, they cancel out. And I'm only left with the top 3, I'm only left with the ones that I'm concerned with. So we have a notation for this. So we are concerned about order here. We're concerned about who finished first, second, and third in this particular example. And we would write this like this. We would go, it's a permutation, and there's 8 total runners, and I'm only concerned about the top 3. So I look at this, and that is saying my permutation, my n, my total number of runners is on the left-hand side, and the number that I am concerned with, which is r, is on the right-hand side. So what I end up with is permutation n to r is equal to, well, it's equal to the factorial of the total divided by the total minus the number I'm concerned with, factorial. So you can see it in our example right here. I had 8 factorial divided by 8 minus 3 factorial is equal to 8 factorial divided by 5 factorial, which is exactly what we did right up here. So one way to do it is to write out all the factorials and cross out all the numbers. And as you might suspect, our calculator will help us do it. I'm going to go 8, which is my n, my total number of runners. And I'm going to go math probability. And if you see number 2 says NPR, that doesn't stand for National Public Radio. It stands for permutations in this particular case. I press 2, and I'm concerned with 3, and I find out that there's 336. And if I went 8 times 7 times 6, 8 times 7 times 6, I find out it's 336. So this takes a little practice, but it's really good. It's essential for working with large numbers like this. So we know that our permutation 8, 3, which if we wanted to say it properly, we would say it's a permutation of 8 objects, 3 at a time, and order counts. Well, from our race example, we know that equals 336. There's 336 ways that might happen out of the 8 runners. But really, if you're thinking about races, yes, I'm concerned. I want the first, second, and third place finishers. They're all going to go to the state meet. But the fact is, it doesn't really matter whether they're all lining up to go in the state meet. It doesn't really matter whether they're 1, 2, and 3, or 3, 1, and 2, or 2, 1, and 3. It doesn't matter what order they're in. I'm really only concerned with, well, who are the top 3, and I don't really care what order they are. Well, I hope you heard me say I don't care what order they are, because that means I'm going to deal with a combination. So if we come back and we think about our permutation 8, 3 was 8 factorial divided by 8 minus 3 factorial, or 8 factorial over 5 factorial. But that gave me all the different orders here of the first 3 finishers. I don't really care about all those the orders of all the top 3 finishers. I don't care what order they're in. So my combination of 8 runners 3 at a time is going to be, well, it's going to be the same as my permutation, except since I don't really care the orders of 1, 2, and 3. I don't care whether it's 1, 2, and 3, or 2, 3, and 1, or 1, 3, and 2. It doesn't make any difference to me. So just like I divided the last time, I'm going to divide by 3 factorial. All these different orders here make no difference to me at all. And since I'm dividing here by another large, another number, it's going to make my number of combinations always less than the number of permutations, which we talked about way in the beginning. So if I write this all out, it's going to be C 8, 3 is equal to, I'm going to go 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then I'm going to divide it by my 5 factorial, 5 times 4 times 3 times 2 times 1, which I am multiplying by my 3 factorial, 3 times 2 times 1. So we can cross out the 5s, 4s, 3s, 2s, and 1s. And I know that this gave us, the numerator here was 336, but now I'm dividing it by 3 times 2 times 1. I'm dividing that by 6, and I find out there's 56 different combinations of 8 objects 3 at a time. Can we use our calculator on this? You betcha. 8, math, probability. Notice number 3 is NCR. So I press 3. I want them 3 at a time. I hit enter, and my answer is 56. So getting the factorials and getting the permutations and combinations, the hardest part is going to figure out, well, what's my N and what's my R? Because once you know that, it's easy just to put it into the right formula. I want to get a pizza, and I go to the pizza place, and I can get 5 toppings from a choice of 12. Do I care what order they're put on my pizza? I don't think so. Well, I mean, I personally kind of like my mushrooms on the top, but let's leave that aside. So this is, I don't care about the order. This is going to be a combination. It's going to be a C, 12, 5. I'm the manager of my softball team. I have 13 people on the roster, but I can only play 9 players at a time. And so I need to set up a batting order for what they're going to be. A batting order. Order matters. So how many different batting lineups, how many different batting orders can I make? It's going to be a permutation. There's 12 objects I'm considering, and I need to find out how many different orders there are to using them in groups of 9. If you can determine the order, whether it's necessary or whether it's not necessary, that's going to tell you whether it's a combination or a permutation. And as long as you kind of have an understanding of this concept of a factorial, giving us all the number of outcomes, these problems really shouldn't be too overwhelming.